Very good morning. And indeed a pleasure to be with you all this morning. Of course, it is, she has just virtually pushed me for this lecture. I was not prepared all these years, last 4 or 5 years, and more into administration. That doesn't mean that I lost touch with the subject. I've been visiting along with her, especially in the Himalayan part, and the topic today that I'm going to speak, the Ophiolites, which are nothing else but slivers of the oceanic crust. Okay, so we through those studies, basically what exactly you understand. I've been basically to a great extent concentrating or more focused kind of a work that we've been doing on understanding the Earth's mantle. And when you say Earth's mantle, obviously you cannot take a trip down to the Earth's interior and pick up the sample, is it not? So there are very few areas wherein the direct mantle samples are available. And then basically the volcanic activity sometimes bring in fragments of the mantle upward. They are called as mantle xenoliths. And they have been actually picked up by mostly alkaline igneous rocks, alkali rich igneous rocks like nephelinite, melanephelinite, basonite, or alkali olivine basalt. Very, I would say, few in number. Volumetrically, if you look at, they do not cover very vast area like the basalts, the Deccan basalt that you see 500,000 square kilometer of area and all that. These generally occur in form of small plugs, all cone-like bodies sort of. But they are interesting because they are rich in volatiles, and therefore those magmas can move much faster, and therefore without giving a chance for the mantle fragment, they are picking up to get interacted with the magma, they are brought to the surface. So accidentally caught up fragments of mantle. That is all. The other area wherein you can get to see the mantle samples is the Ophiolites. Wherein basically you have a mantle but characteristically different in character. Okay. So we'll speak about that little later as such. I'm pretty sure that the expert who has come from France has spoken much about the plate tectonics, tectonic aspects, and so on and so forth. So by now it must be very clear to you all that the Earth's outermost part has been fragmented into number of plates, and these plates are moving in different directions. And basically the movement is happening, basically the reason being, this is the only living planet, means active planet. The rest all the planet in this solar system you look at, they are all dead planets. Okay. Why this is living? Not because we are living on it. It is living only because the mantle is very hot. And the mantle is hot, it's not consolidated, it's not completely solidified. And therefore the heat that is dissipating, coming out to a great extent, carries out the relative motion of the plates. So that's how the plates move in different directions. And then when they are moving in different directions, so obviously if one is moving towards north and from the opposite side if there is a plate moving towards south, eventually what is going to happen, they are going to get collided with each other. In between the two plates normally you have a development of oceanic basins. Oceans is called the Wilson cycle. Closing of ocean basins, opening of ocean basin, basically when the contents are moving away from each other, they are called as a divergent sort of a plates. And then the convergent where they are moving towards each other. And when they move towards each other, obviously what will happen eventually, the intervening oceanic basin that would get closed completely. Means what? Basically from there would be a migration. We'll come to that little later. An interesting part of the ocean basin being basically in the central part, you have a volcanic activity constantly happening. Although we don't notice it, it is on a regular basis, day-to-day basis, minute-to-minute basis. There is a huge fracture in the middle part, what is called as a mid-ocean ridge. And mid-ocean ridge is the place where you have the generation of a new crust. When we speak about crust, general classification for crust basically a continental crust and oceanic crust. This is the general classification as such. And they do differ considerably in their physical attributes as well as the chemical attributes. If you look at the continental crust, generally, if you look at the age of the oldest so far preserved continental crust could be few billions of years, like the Archean crust that we speak of, 3.4, 3.5 billion years. If you think of the Indian subcontinent, when we start moving towards south, you get to see the older rocks, age-wise older rocks getting exposed. The Dharwar Craton, the granulite, the charnokites, all those kind of rock that you see actually represent basically the oldest part of the continental crust. If you look at the overall composition of the continental crust, it's more granodioritic in composition. So it is more towards like, if you look at the mineral composition, more felsic minerals, more Si rich, Al rich minerals as such, okay. So plagioclase and whatnot, like various different minerals that make. And the continental crust basically being made of these lighter minerals, they are not very heavy and therefore they rarely get involved into the process of subduction. Subduction is basically when the two plates are colliding with each other, depending upon the density contrast, one plate will curl downward and start moving beneath the other plate. So that kind of basically collision, if there is a two continental land masses colliding with each other, rarely the continental crust gets subducted. And therefore, you have the oldest crust preserved against the oceanic crust. Oceanic crust, after its birth at the mid-ocean ridge, is destined to get destroyed. So the oldest oceanic crust that you have is perhaps Jurassic, not more than that. Because whatever that got created eventually got destroyed. Why? The reason being it is more dense in character. And the density obviously is governed by the mineralogy. So more dense mineral, basically rich in FeMg, like olivine, pyroxenes, spinel, garnet, those basically make the composition of the oceanic crust, therefore it is dense. Against that, the continental crust keeps on accumulating as such. And therefore, even if you look at the thickness of the continental crust, in places it exceeds hundreds of kilometers. In India, obviously, when you go down towards south as such, the continental crustal thickness to a great extent measured by the indirect means like the geophysical means is about say 60, 65, 70 kilometers as such. When you could come towards the coastal part, the marginal part, the thickness is relatively low. So you generally get to see the mantle upwelling, mantle has come up, in the sense the crust is thin. So there it could be 20 kilometers, 30 kilometers, 17 kilometers likewise. And especially those are the areas where you have relatively low thickness, those are basically the tectonically perhaps very significant areas. Somewhere something has happened. Perhaps if you look at the coastal part of Maharashtra, Alibag and then all those different areas that you look at, generally the crustal thickness out there is comparatively low. At the same time, all along that, you get to see basically an array of hot springs, from roughly around 32, which are presently very active. Some of them, the temperature has gone down. but some of them are very active. So the groundwater that is getting heated up, and because again it becomes buoyant in character, being lighter, so it starts coming up, and in the form of hot spring you get to see them. What does that indicate? Again, basically the mantle is relatively has come to a shallow depth out there. And why is it so? Because it has something to do with breaking of some portion which was attached to the western margin, perhaps the Sayadimala, the Seychelles, the Madagascar, which were part and parcel of the western part of India. So it got broken away. Okay. So there the breaking is not because of this, the kind of plate tectonic that we are speaking of. Over there basically it's breaking basically because of the Deccan volcanic activity as such. Deccan volcanic activity. That again is a hot spot basically, or a mantle with a higher temperature pinging down from below like a stove and something on the top, and then it got broken up sort of. But here the things are different. At the mid-oceanic ridges, obviously these are two plates which to a great extent, because the mantle is rising up, and when it comes to a shallower depth, what will happen? There would be a reduction in pressure, and there as well as reduction in temperature also. But the temperature loss is not very significant, and therefore it undergoes partial melting. If you intend to melt a mantle, two parameters that you need to govern: either you raise the temperature or you reduce the pressure. So that is what happens over here when the mantle, and it is upper mantle. See, time is little less. I cannot, the thing that I teach for the entire semester, I cannot concise it in just one hour lecture as such. So there basically I am just giving you a conceptual understanding. Okay. So the mantle basically which is rising at the mid-oceanic ridges is upper mantle, and upper mantle is depleted mantle. Depleted mantle in the sense with respect to its ingredients. There is an enriched mantle and there is depleted mantle. There is a sterile mantle and there is a fertile mantle. What do you mean by that? So basically, fertile, it is still fertile, it can produce magma. So it has all the required spices or the ingredient that can generate a new material. And the mantle which is depleted has lost its capacity, or rather lost its spices, ingredients to produce any magma. This is what is basically the difference between sterile mantle and the fertile mantle, or enriched mantle or depleted mantle. Enriched means it is enriched with respect to those elements which to an extent would get partitioned into magma. So new magma, new sort of a material gets produced as such. So relatively the more mantle that we call is comparatively, relatively it is a depleted mantle. But when it comes up, shallows up, comes to a shallower depth, it undergoes partial melting. And in that partial melting process, what is happening is basically the magma gets pulled up in a chamber. These are again concepts that we have. So chamber is something like, it's not something a permanent kind of a thing that has been created, a hollow wherein the magma starts getting accumulated as such. And then when magma comes and gets accumulated there, you have the process of what is called the differentiation, magmatic differentiation. So the first minerals crystallized which are heavy, relatively denser one, would get formed, get settled onto the floor of magma chamber, creating a layer. Okay. This process is continuous, so there is a continuous supply of magma that is happening. So there is a turbulence that is happening. So certain minerals are kept in suspension, the lighter one, but the heavier one, they will settle down. And that's how you would get to see a kind of a layered structure. As the magma moves from the mid-ocean ridge away from the axis, the cooling will start and you will have creation of various different layers as such. So, the oceanic crust generally is seen to be a 4-layered structure. It has 4 different layers. Okay. And what are those 4 different layers? We will come to that a little later. And then from that chamber, whatever lava that comes up, comes in direct contact with the oceanic water, it would get suddenly chilled and you will have creation of the topmost layer, what are called as the pillow lavas. Okay. So, the pillows, then perhaps down below that you have the basaltic lavas, then you have the gabbro to a great extent, which is a basic material being consolidated at a greater depth. So, comparatively coarse grain, homogeneous in character, homogeneous in texture. Down below that you will have a layered gabbros. So, alternate bands of say lighter minerals and darker minerals. So, heavier and lighter minerals. So, that kind of a structure would be created, that is called a layered gabbros. Then down below that you will have layered peridotites. So, dunite alternating basically maybe with pyroxenite, alternating with Habsburgite, Verlites and so on and so forth. So, what are these names I am taking? Basically these are based on the presence of peculiar minerals, absence of peculiar minerals. We will not get into all that jargon, but it would be a layered structure. Okay. And down below that is the mantle. So, that is the 4th layer that you, and on top you will have basically the deep water oceanic sediments, pelagic sediment that we call, and then this is the kind of a structure that get created. This is what is the oceanic crust, which is comparatively very relatively it is thin in nature. 6 kilometers, on an average 7 kilometers. It could be 11 kilometers, it could be slightly lesser than that, lesser than 4 kilometers, 5 kilometers. But it moves away because every time the magma is pushing through that mid-ocean ridge axis coming up and all that and pushing that plate material away from it. So, eventually this oceanic crust is going to get migrated from the axis. So, somewhere when there is another plate from the opposite direction coming up, so what will eventually happen, there would be a collision and this oceanic crust would get subducted downward because it is heavy. It curves down, bends down and starts a journey downward. How deep does it go? Based on again certain characteristic features of peculiar rocks, the chemistry that we actually are more interested in studying. So, it goes to 660 kilometers seismic discontinuity. That is the travel distance basically. It can go down to almost 660 kilometers, perhaps maybe going down beyond that. But we have no tool to track that journey, or perhaps the temperature is so high out there that whatever is going down gets completely melted, gets mingled up, get mixed up with the stuff present at 660 kilometers. But basically 660 kilometers seismic discontinuity is being reflected through this seismic studies. We can understand there is some change, density contrast that is happening. So, up to 660 kilometers the journey people have understood. But not entire of the oceanic crust gets subducted. It so happens sometimes it slide past, instead of going down, it get dragged and get transported onto the adjoining continental margin. Okay. And where it get preserved. So, some portion, slivers I would say, or fraction of that oceanic crust which escapes subduction and slide past and get transported onto the adjoining continental margin, a process opposite of subduction, what is called as abduction. It got abducted onto there, and that get preserved in the orogenic belt, and that is what basically you've been studying throughout this 6-7 years, different kinds of orogenic that you have, and get preserved basically in the mountain building activity that goes on onto the adjoining continental margin. And that's how they provide you an opportunity without taking a trip down to the ocean surface. You can see the oceanic crust preserved. Okay. This is what actually got noticed in the first ophiolite sequence that got reported through those ophiolites from Cyprus, and since then people started looking for such sequences in orogenic regions, mountain belts basically. So you have the, in fact there is a Penrose conference wherein this nomenclature got decided, why it is called the ophiolite. Ophi being basically a Greek terminology meaning serpent skin like texture. Serpent skin like texture. Why is it so? Because it's constantly the ultramafic matter constantly in contact with oceanic water, so it gets altered, gets serpentinized, and therefore serpent skin like texture or surface it has. And that's called as a trinity. There are three different rock types combined together: the radiolar insured, the pelagic sediments, the volcanic rocks, and the ultramafic rocks. So the terminology got established in the Penrose conference, and subsequent to that people started looking at it. It's been 40 years I've been visiting Himalayas. So I did my PhD on the ultramafic rocks from the Dras and Kargil region. You all people are familiar with these two names because of the Kargil war. Prior that, no one knew about these two places. Dras is considered to be the second coldest place on the earth after Siberia, and the minimum temperature that was recorded was something to the tune of minus 70 degrees centigrade. Okay. So exactly I would say 40 years before time, way back in 1985, I made my first trip to Dras. Okay. And those days there were no flights, so the travel time used to be 6 days from Pune. So you start with the Jhelum Express, next morning you reach Jammu. Jammu generally you reach by 10:30, 9 o'clock, 10:30, 11 in the morning. The bus that leaves basically for Srinagar, the last bus is at 8:30 in the morning. So you stay over, next morning you catch the bus, go to Srinagar, and then there is a bus to Leh every alternate 3 days. So if you are fortunate, you would get the very next day, otherwise you get to stay at Srinagar. From there is about say 60-70 odd kilometers journey, which takes about 6 hours, because you pass through a ghat section called Zojila Pass. In those days it used to be a very singular kind of a track and mostly meant for army. So the general people was a second priority. It was meant for the army transport, okay, because you all know that up to Leh Ladakh we have army settlement, and obviously the resources that are required for their living get transported from Srinagar all the way to Leh. These days now there are flights, so some material also come from Chandigarh. Okay. So that was the situation 40 years before time. Now if you intend to, you can start from Pune, and the very same day you can reach Dras. Okay. Or you are all fortunate people. Okay. So things have changed considerably. You can, in fact, that is what we make. Every September we make it to generally to Leh Ladakh. The reason being the tourist season is over, because the winter starts setting in, and therefore the prices goes down. And for a student, obviously, although he likes to travel, doesn't want to spend, because the spending comes from the parents' pockets. Okay, so you are dependent on someone. So considering that fact, we generally travel little late, but it is very cold out there. And then we spend about 10-15 days. Every year it has been a regular feature. Last year also we traveled. The interesting part is basically to look for these slivers of the oceanic crust, and the ocean basically was the Tethys Ocean. You all know the story, like in between the Eurasian plate, is it not, and the Indian plate, there used to be an ocean basin called Tethys Ocean, and the water after the collision of these two continental land masses, obviously you all know that opening of the Mediterranean Sea. But the oceanic crust basically, which got uplifted, created the mountain chain, what is called the youngest mountain chain, youngest, loftiest, highest, tallest, youngest. That is the Himalayan mountain chain that you have. And then obviously tectonically, if you look at, you generally get to see crustal dislocations, rupturing of the crust into various different zones. So those are called the fault lines or thrust lines. And since the plate has moved northerly, so whatever material that has getting, say, deposited with a southward push, so everything is moving towards southwest. So between the two major lithologies, you will have a major crustal dislocations, and that has been identified, and those accordingly the Himalayas has been divided into lower sub-Himalayas, lower Himalayas, middle Himalayas, upper Himalayas, and so on and so forth as such. Okay. So this is what is in nutshell the story of Ophiolites. Story of Ophiolites. Ophiolites are interesting, important, because they to a great extent speaks about, or rather gives an understanding about the oceanic crust, its character, but at the same time gives an insight into the mountain building activities, because they are preserved there. So keeping that thing in mind, we have been studying these rocks. So Malika probably must have talked on Mar, mid-ocean ridge basalts. So Marbs, I do not know whether, yeah, okay. But Marbs and Ophiolites are no different. They are one and the same lake. It's a four-layered structure. Marb is only the basalt component that we are looking at, whereas basically the entire section that we look at, that is what is called as an ophiolite. So this is how it looks like. On the top, you have the pelagic sediment, deep water oceanic sediments. So a thin layer of sedimentary material. They are radial in sherds. This is what basically has been seen topping. Then you can have the pillow lavas. Then you have the sheeted dike complex. So the magma to come up in the form of a volcano, you require to have some conduit, some fracture, is it not? The plumbing system, transportation. So those are the cracks and crevices through which the material comes up. And eventually, those act as basically the gutters or the channel through which the magma is moving up. Eventually, the magma would get consolidated in the cracks itself and giving what is called as a rock that is generally in the field we recognize it as dike. Dike is nothing else but a conduit, a fracture through which the magma was transported to the surface. So you have many such cracks, and it is very interesting. Over here, what is interesting being generally in a solid rock mass, magma is making first of all a fracture. It gets widened up. So and the magma when comes in contact with the cooler surroundings, obviously there is a sudden chilling. Chilling means fining, say glass kind of a development that happens. So generally dikes, if you look at the marginal part, are very fine grained. In the middle part is comparatively little coarse grained as such. Okay. So we call them as chilled margins. How do you identify a dike? On the basis of the chilled margins. Okay. Interestingly over here, these dikes, so obviously dike should have two chilled margins, this side and the other side. Here it is so interesting, the dikes have only one chilled margin, because the same crack got activated time and again. So one crack got opened up, magma came into it and it pushed, another basically coming into. So every time there is a thermal contrast that you get to see. One side little colder, the other side is still very hot. And that's how the margins are, actually the dike is also getting split into two, and the dike is also moving away from each other, is it not? So one margin is going towards the other side, the other margin going towards the other side. But in C2 dike, if you look at, it will have only one single margin as a chilled margin. And then it creates a sheets like structure. Therefore, it is sheeted dike complex. Then down below is the magma chamber. So where you are getting into the isotropic gabbros. And gabbros, again, compositionally, there can be a different varieties, troctolites, norites, okay, or normal gabbro kind of thing. These, I will not get into the jargons of names, because those names, to a great extent, the naming happens only looking at the characters, no? घर में नेमिंग सेरेमनी होता है ना, बच्चा नया पैदा होता है तो कुछ तो माँ बाप सोच के उसको नाम देते हैं ना. यहाँ नाम दिया जाता है based on basically the mineralogy they carry, the place they were first reported. All these names, dunite, pyroxenite, all these names, if you look at, they are actually names of the first locality where they got first identified. So that is how the naming happens over here. So here the compositional diversity also to a great extent decides the nomenclature. And then comes the chemistry. Chemistry, obviously we go down to from the major oxide, because major oxide to a great extent get changed considerably with respect to its interaction with water, with other thing and all that. So major oxide doesn't tell you much about, therefore you go for basically what is called as a trace element geochemistry. And then these days you can measure the isotopes also, and that is a very robust technique, because isotopes do not get changed. So the original DNA of the rock can be understood on the basis of the isotopes. Within the trace element you can have compatible trace element, incompatible trace element. Compatibility means two persons sitting together, they sit together, eat together, move together. So there is a compatibility, no? They are comfortable with each other. That is how the friendship happens. Same, nature follows the same rule everywhere. Here also certain elements have compatibility for certain specific minerals. So they are happy with only those minerals. The reason being basically, again, the further characters, the ionic radius, the charge the element carry, and so on and so forth. So they do not get fit into the given structure. Therefore, they are expelled out and get into the magma. And therefore, trace element geochemistry is interesting and important, because to a great extent you can track the overall sort of evolution of the rock that has undergone. And therefore, these days people more, you can have such beautiful sort of a graph created sort of on the basis of the trace element, and understand basically the kind of differentiation, evolution the rock has undergone. Okay. Textures obviously speaks about the conditions under which the magma has cooled. So more coarse grained, coarse texture obviously indicates a slow cooling. So if it is the cooling is happening in the magma chamber itself, it is not getting exposed to the atmospheric conditions, no chilling, it has enough time to cool down. So it cools down, and then you can have a larger crystals growing in larger size as such, and depending upon obviously the composition, either they will float or settle down. Heavier one like olivine, pyroxene, spinel, garnet, these are all basically dense minerals. They settle down onto the floor of the magma chamber. The lighter ones, perhaps the plagioclase, feldspar. So feldspar, more felsic minerals, like they would float in the magma chamber. And eventually when whole thing moves away from the mid-ocean ridge axis, there is a complete consolidation that happens. First of all, there is a temperature contrast also. Down below there is a hot stove, like the magma is constantly coming up. Up, the cooler surface, is it not? So this thermal contrast in fact creates what is called as density currents, is it not? So the magma is continuously gets stirred, and this stirring to a great extent, the heavier one will settle down, the lighter one would be kept in suspension, floating sort of. What I am trying to tell you, how this 4-layer structure gets formed. This is what is very interesting. And that 4-layer structure initially was seen at Troodos Massif in Cyprus, and this was something of this kind, like this is a 4-layer structure. Down below you have an ultramafic unit, then you have the pointer chal raha hai kya iska? Nahi. So you have a layered gabbros, you have basically the ultramafic unit. Ultramafic means rich in Fe and Mg. Okay. Then you have the layered gabbros, so pyroxenite alternating with say anorthosites or alternate layers of plagioclase, and then perhaps the other mafic mineral, maybe olivine or maybe pyroxene. Then you have isotropic gabbros, no layering. So they are all mixed up sort of. Then you have the sheeted dikes that I spoke of, and then on top obviously what you have is the pillow lavas, and sometimes you also get to see a more differentiated metal, more felsic in character, granites basically, plagiogranite they are called as, they also. So this whole structure is ophiolite. Ophiolite is a 4-layered structure. And then, so therefore an ophiolite is a section of Earth's oceanic crust and the underlying lithospheric mantle that has been uplifted, abducted, and often emplaced onto continental margins or in accretionary prisms and island arcs. Okay. Mantle unit, ultramafic complex, basically dunites, Harzburgite, larzolite, and associated. There can be a mineralization also. Sometimes you can have minerals of economic importance associated with it. You can have a chromite. You can have some basically some interesting other minerals, elements also. Unfortunately, India, in the Himalayan part, although we have chromite, but it is not enough in its volume. It's not mineable. So when you call it economic deposit, it has to be economic. So the money that is spent on exploiting that particular resource and the money earned after selling it, there has to be profit involved, no? When that doesn't happen, so it is just of economic interest, we call it. Mineralization of economic interest, but there is no per se economy attached to it. So we don't call it the economic deposit as such. And the reasons are obvious. Obviously, it is present in a remote area, far away from transportation, going to be difficult. climate basically is not supporting kind of a thing. So the labor and all that is going to be very expensive. So even otherwise also if the volume is large, it's not going to get economically exploited as such. So it is merely of academic interest. So sometimes we do get, and these names that I say, dunite is a monomineralic rocks made up of one single mineral, olivine. Second name is Habsburgite, olivine and one kind of a pyroxene is called the orthopyroxene. Lerzolite, it has both the pyroxene, clino and ortho. So this is what is interesting. Lerzolite is the most enriched material. It's the enriched mantle. Okay. Enriched mantle means basically it has all the ingredients. So when it is subjected to the melting process, what it loses basically the clinopyroxene. And clinopyroxene mostly hosts all the trace element inventory. So when the magma is generated, clinopyroxene get completely consumed. So what is left over here is olivine and orthopyroxene. So it is a depleted mantle. So it is a leftover. It is a residual mantle, residue that is left over. So these are the terms that people make use of, residual mantle or depleted mantle. Yeah. And then dunite is monomineralic. So even the orthopyroxene is also removed. Temperature wise, if you start looking at the melting temperature, olivine perhaps has the highest melting temperature as compared to the clino and ortho. So the first one to get melted is going to be clino, second ortho, and rarely you cannot achieve a temperature of the order of some 1600 degrees centigrade, which is the melting temperature of olivine, and therefore olivine rarely gets involved into the melting process. But it is again interesting, it is not whole rock melting. Melting always happens at the contact level, all three minerals. So relatively basically some portion of even olivine also gets pushed into, but otherwise entire of clinopyroxene, a moderate amount of ortho and very less amount of olivine. That is again how the melting happens and all that. That's another interesting sort of a story, and to come to understand that it would be another 7-8 days lecture series sort of. Okay. So Moho transition zone. So from crust, this is what is the crust, the 4-layer structure that you are looking at is the oceanic crust. Down below that there is a sudden jump in the P wave velocity. Means you are entering into a material which is more denser in nature, and that is what is the mantle. Okay. So that is what is because of Mohorovicic discontinuity. On the continental side, the Moho can be as deep as I said, Dharwar and other places. If you go to, the Moho is situated at 70, 60 kilometers because the crustal thickness is very high out there. In the oceanic regime, obviously, as it is, the crust has a limited thickness. So 7-8 kilometers, that's the maximum, and then you get into the mantle patterns. But in between, there are transitions. It's not something like a compartment. You draw a line, no. Beyond this is all mantle. It's transitional. So things happen transitionally, sort of. Okay. It's not sudden, sort of. So in between you will have rocks which shows characters typical of partly of the mantle and partly of the crust. So that is what is called the transition zone. So it's not sudden, it can be 3-4 kilometers, 2 kilometers of a layer wherein you have a rocks having sort of a characters, mixed characters. You cannot decipher whether it is exactly a mantle material or crustal material. Okay. That is what is called as a transition zone. And this is what is interesting. Another interesting thing that you get to see, generally speaking, in the continental side, you have only one single Moho. One single Moho, is it not? Here you have two kinds of moho. One is seismic moho and second is called the petrological moho. Because the layered peridotite, they are peridotites only. So the mineralogically speaking, the composition remain the same, but petrologically they represent the continental, the oceanic crustal material. It is they are generated out of a igneous process. So petrographically and chemistry wise they are distinctly different from the mantle. So you have two mohos. One is called as seismic moho, other one is called a petrological moho. And petrological moho is basically the characteristic of the transition zone. Okay. So over here you can see crustal unit has been represented by gabbroic complexes, sheeted dike complexes, pillow basalts, associated rock units, sedimentary units, felsic units and metamorphic soil. Coming to basically the types of ophiolites. So where they are generated. The setting, people call it the tectonic setting. Okay. So subduction unrelated, MOR, plume type and continental margin type. And then second one is called subduction related and supra-subduction zones basically, SSZ. We have no time to get into all those minute details, but this is generally the picture that makes things very clear. So this is what is called as a mid-ocean ridge, where generally you get to see the formation of oceanic crust. You can see upwelling, the mantle is coming up. Okay. When it comes to a shallow depth, it undergoes partial melting, creation of volcanic material, and this oceanic volcanic material is going to push the plate this side, okay, either side. And this mid-ocean, you can see eventually this is the continental landmass with which the collision is happening. And what will happen? The oceanic crust would get dragged down and partly get abducted onto the adjoining continental landmass. So that those are the orogenic mountain chains, the Himalaya for example, and that's how basically people go and study those things. So these are basically some cartoons explaining the various different types. If you look at generally ophiolite distribution in the Indian context, extrapeninsular Mesozoic ophiolites along the ITS-Z, Ladakh, Naga Manipur ophiolite belt, Andaman Nicobar ophiolite belt, and there are peninsular ophiolite. During even the older time, Proterozoic and Archean also, you had something similar that was happening maybe on not very large scale, but on a smaller scale. And this is what, this is where you can see, this is the Indian subcontinent, and here the green line that you are looking at, this is what is called as the Indus-Tsangpo suture zone. Suture is the line of collision between two plates, and it's called as Indus-Tsangpo because it's following, the two rivers are following the same course. Indus and Tsangpo is coming from the Tibetan part as such. So therefore it is called the Indus-Tsangpo suture zone. And then along the Indus-Tsangpo suture zone, you have presence of sort of a preserved slices or slivers of the oceanic crust, and that is what I began with in 1985, followed by Malika, 2000 perhaps. Yeah, then subsequent another lady she worked on, and then perhaps he is my grandson sitting there. He is following the fourth generation. Okay, so he is looking into a different aspect, not necessarily ultramafic, but maybe the granitic rocks and associated mineralization, the pegmatites and so and so. So which to a great extent have the potential of mineralization. Incidentally and unfortunately, the most mineralized part is occupied by Pakistan. We don't get to see anything very interesting on our part. Baluch and all that, and there is a fight that is happening presently also. The Balochistan is those freedom fighters. They are opposing the Pakistanis for exploiting their mineral resources. In our part, basically, so far we have not come across very intensive kind of a mineralization, because subduction zones are otherwise the locales of intensive strategic mineralization. There can be copper, there can be tin, there can be tungsten, okay. But we are not fortunate. We don't have that. Probably the reason being, obviously, what is the kind of crust that got subducted? A more enriched crust, if gets subducted, perhaps there is more chance of getting more mineralization. More older crust, so older obviously is more richer. If that gets subducted, obviously it would get into the magma, and the magma perhaps would provide the necessary kind of a mineralization. So this is again interesting, why mineralization is not present. So what is the kind of material that got subducted? And incidentally, it is not the oceanic crust alone, it dragged down along with it the continental portion also. Even the continental portion got dragged into the subduction. This is what Mallika worked on, and then those are basically the continental crust when get dragged down, goes down, but it is buoyant in character, forcibility has been pushed inside, but eventually it would bounce back. But as it is going down, obviously there is change in temperature, pressure, so you will have a rock similar to the ultramafic, differing in composition. Those are called as eclogites. Seismically, their characters matches more or less well with the seismic characters of the mantle material, but otherwise compositionally they are distinctly different. Eclogites, okay. And when the continental crust being lighter, being buoyant in character, it bounces back, there can be a retrogradation. So there is metamorphism that is happening, burial kind of a thing, as it is getting dragged into, but it escapes certain phases in between, and accidentally those eclogite can be brought to the surface as it is without much of a change as such. And that is what she worked on, a place called Somarari, crystalline acidic kind of a material over there, wherein you have enclaves of those eclogite. So that tells you about, when you understand the temperature pressure condition, you can to an extent understand how deep was the continental crust driven, how deep it was driven into the subduction zone, and that goes almost up to 100 kilometers. Huh? Yeah, so she spoke about that. Okay, and this is what the, perhaps you are again familiar with this picture. This is the Himalayan part. Last almost week and more, all these pictures are shown on the TV. So we are basically moving from northwestern part to the eastern part, and all those red thing that we are looking at, the red portion, is the slivers of oceanic crust, Ophiolites as such. Okay, so all along its length, more than 600 odd kilometers, from say Dras in the Dras in the northwestern part to almost a place called Tibetan part. What is that? I'm forgetting. I'm forgetting the name. So basically all along this you have the preservation of this, and this is what we have been concentrating for so many years. So there is a Nidar ophiolite, this is Pongtang ophiolite. So you can see they have a peculiar sort of a trend, a linear in character. This is what is the suture, all along the suture. But some pieces actually are thrown vertically up. So autochthonous, allochthonous, different terms are there, probably in tectonics, structural, while doing the structural geology. So nappe, clippe and all that, klippen and nappen and all that thing. So a sort of a material been uprooted and then thrown at a larger distance. Okay, allochthonous, autochthonous. So you have this Spongtang ophiolite. You can see, in fact, this is the place where all along you get to see, and this Spongtang is much at a height of almost 4,000, 5,000 meters?
54.
No, meters.
54. Spongtang is at 54.
Yeah, 5,400 meters, that is the height where it has been thrown up. Okay. So you got to climb up and then pick up those samples. Okay. Then the other place is, as I said, Drash, and these are the crustal dislocation that I'm telling you basically. Sub-Himalayan part, and you can see, in fact, normal fault, thrust fault and all that. MFT, main frontal thrust, main boundary thrust, main central thrust. That is how basically the Himalayas are divided into low sub-Himalayas, Siva lakes, upper Himalayas, middle Himalayas, and so on and so forth, the higher Himalayas or trans-Himalayas. You got to stop me somewhere. Huh? 5-10 minutes. So this is the mantle section that is coming from Oman. Okay. So here, of course, this is the entire landmass that you're looking at. You don't get to see all the different layers in this picture. It is more of a panoramic view, you can call it. So this is all basically Harzburgite, the residual mantle or residual portion of the mantle or the oceanic crust. This is called as a fragments of uppermost mantle trapped in mountain belts coming from the Oman region. This is coming from our own region. This is the Nidar ophiolite. Nidar ophiolite. Okay. And Nidar basically you can see, in fact you can see, very interesting. This is a small slice. Okay. It is sitting on sediments. You can see the contrast also. A small sort of a slice. This is peculiarly of a pyroxenite, and all these are sediments over here. And this is sitting over again a sedimentary rock. Okay. So a fragment of the uppermost mantle trapped in mountain belts, India. This is the layered peridotite that I was speaking about. So you can see a very crude kind of layering that one can see basically. So this is obviously the feature that got generated because of the magma underwent differentiation in the magma chamber. So that's how creating this kind of layering. It's not going to be like something that you see in textbook as it is, you would be able to see it in the field. Okay. You got to develop an eye for it. It's not with the very first day you'll get everything and just first year fieldwork done, complete PhD, next year submission. That doesn't happen. Means just to tell you a story, someone told me that there are mantle fragments, mantle generalists in the Kutch region. So like you had the dogs, no? This. So I was virtually going on in all those areas like a dog, sneezing everything like here and there. And then to my surprise, the fragments were so small, so a centimeter. When I got them, I was excited, but at the same time, I said, what I am going to do with this? Neither you can separate it out, nor you can crush. How am I going to study the chemistry? How am I going to study the petrology? And to my fortune, after 6 months, another gentleman from Macquarie University, Sydney, Professor Bill Griffin, I kept on writing to people like, I have this material, very exciting, but very small in size. How do I work on this? So then I received a letter and he called me. He said, I have an instrument, and wherein on that scale also you can analyze them samples. So that is called the LAICPMS, laser ablation inductively coupled plasma mass spectrometer. So that I saw in way back 1998, and that dream I followed. When can I bring this machine to my land? And when fortunately when I became vice chancellor, the first thing that I bought for the central instrumentation facility was the LAIC. Basically, through a laser, you can make a small sort of a hole into the mineral. It's a dent kind of a thing. See, 60 mu, 40 mu deep. And that portion is subjected to the mass spectrometer. So even you can analyze diamonds. And then after looking at that facility, prior to Mallika, I had another student named Sonal Rege. And she was all the time very bubbling kind of a girl, very short, but had interest in gemology, and that too in diamonds. I said, who will allow you to work on diamonds here? And then I sent her to Macquarie, and then they worked on diamonds. And they actually worked on diamonds, that too of gem quality. Otherwise, no one would give me a diamond of gem quality. Because of this particular technique, it was feasible on the surface, a small scratch kind of a thing. And then they resolved a issue that's called as, you all are aware perhaps, diamond that those generally called as blood diamonds or conflict diamonds. So in Africa, from certain part, those diamonds which are mined actually goes into the wrong hands, and the money that is earned is used for antisocial activities like terrorism and all that. So how do we stop the entry of those diamonds? So making use of this instrument, a forensic kind of a science you can call it, DBS and Rio Tinto, these are the two major players, and they have a command and control over the diamonds world over. So DBS actually provided the samples from the entire globe, and on the basis of geochemistry we could pick up, because every diamond coming from a different sort of a continental landmass has different characters. So the chemistry was made use of in isolating those diamonds coming from the Central African region, Congo. And that's how we could stop the entry of those diamonds. Then later on there was a Kimberley process and all that. Now it is made very compulsory that while buying diamond also, they have to tell you where from it is coming, where, how it was brought here and all that. So the entire history is made visible to you, then only you can buy it. But those days it wasn't. So to stop the entry of such diamonds, which are called as blood diamonds or conflict diamonds, we made use of this particular instrument. And she did her PhD on that. And now she is at France running her own laboratory. Okay. So this is a peculiar sort of a Habsburgite. Again, I will not use the term, the depleted mantle. And then from surface I can't make out what is it made of. So I have to make a thin section, a slice of it, put it under microscope, and then you get to see this such kind of an exciting picture. Okay, so you can see these are all dark colored minerals, olivine basically, intensively fractured and all that. Okay, And then basically, since they are coming from deeper regions, so they will always show stress features. They're always very strained, is it not? When a person gets stressed, so obviously what happens? Strain, is it not? It is the response to the stress that is applied to. Okay. So these rocks also either get, minerals get either fractured or completely, to a great extent, get, I would say, stress. So they change their optical properties. We'll maybe, if I have pictures, and try to show you. This is another fragment basically, and this is me who is standing over here. This is again coming from the Nidar part. This is the pyroxenite again at Nidar. This is what perhaps Mallika must have shown you. These are the eclogites, basically the continental material that has been preserved as enclaves. This is coming from basically the Somorari mountain chain at Sumdo, and perhaps again this is me only, very young. And these are the enclaves. So sometime way back, maybe 20-25 years before time, and these are the enclaves that we could pick up and we could study them. She worked on the temperature pressure conditions and could end up in actually end up basically tracking the journey of the Indian continental landmass. It went down to almost 100 kilometers down below. So a closer picture of the same eclogites, ophiolite types. This is coming from the Dras region. Okay, so the Kargil war was fought here. This is the Orange Hill, and adjoining to it, the what is called as the other hill, Kargil, Tiger Hill. There are 3 hills in fact. So this is orange in color. The reason being obviously the olivine undergoes alteration and provide this kind of a tinge. So from a distance you can make out a huge sort of a sheet of ultramafic material, ultramafic unit as such, roughly around 5 kilometers in length, 2.5 kilometers in width, and sitting on basically sedimentary rocks. So from that you can make out this has come from somewhere and been thrown here. Okay, so these are some of the pictures of those. And then very interesting, as I said, you can sometimes get mineralization. So this is the chromite basically, and again this chromite exhibit a typical structure. It's called a pod-like structure, therefore it's a podiform structure, podiform and layered banded chromite. So you have a chromite mineralization, but of no use. Then these are the Varroites and Websterites. Again, it's me there, me. And these are basically, you can see, get to see, these are the dichelates in fact, and you can get to see some interesting sort of a structure that get created. This is the kind of a layering that I was talking about. These are the layered gabbros present over there. Then this is the honeycomb kind of structure that you get to see. It's a larger porphyritic, basically pyroxene getting altered to amphiboles. And then this is what a very coarse grain gabbro, indicating basically a much cooler kind of a cooling. A prolonged time was available for the magma to get cooled. These are the fine grained one, obviously, much faster, didn't wait very much, they were in hurry basically. So obviously very fine grained kind of a thing. And then the granites over there carry fragments of, so that is again a indication that the granite got emplaced later, because you get to see the enclaves of these gabbros, the previous one, more or less. These are the crustal fragments, crustal, you can call crustal xenolis, preserved in the granitic rock over there. Then this is the Trinity Ophiolite from USA. and then troctolites and mantle peridotite. You can in fact, so that's how the one presently Malika is working on is the Spongthang ophiolite, and this is the Spongthang unit. You can see at a height of about 5,400 meters from the mean sea level. This is the geological map, and this is basically the field pictures. Okay. So this is the ultramorphic unit, again showing the layering and the chromite and thing like, and then the textures. I think I have bored you enough, so I will not get into again those minute details. Maybe sometime, because you are going to be here, Oliver is leaving, is it not? You are going to be here, so maybe some extra lecture when time permits on the chemistry and other minute detailing. Okay. So thank you so very much. First of all, thanks to Malika, Oliver for tolerating me for so long. Thank you so very much. We'll meet again. Yeah.